All right, welcome back to 9.4. We are moving on to different identities today. We're looking at Pythagorean identities. You might have seen this before in pre-calc 11. We'll see, but it's not something that's you know totally new. I guess I might have introduced this to you anyways in the past. So here it says in this unit circle below, explain why sine squared theta plus cosine squared theta is equal to 1. This equation is an identity. Why do you think it's called Pythagorean theorem? Well, this has to do with this unit circle right here. And really, we have seen it before that, unit circle means the radius is 1. And recall, this is the x value, and that's the y value. Okay, and recall, I think I mentioned this to you earlier, the x value representing the cosine theta, sine theta is the y value. So if you look at this triangle and if you use Pythagorean theorem, let me just blow this triangle up a little bit here. That's x, and that's y, and that's 1. We know that x squared plus y squared is equal to 1 squared. Right? And 1 squared simply is just 1, so I'm just going to write it as 1. And again, based on this, x is simply cosine, so you have cosine squared theta plus sine squared theta equals to 1. And there is our Pythagorean identity. And yeah, that's it. It's pretty straightforward. However, there are variations of it. I mean, this is the basic Pythagorean identities, but you can actually manipulate and you actually can get either this form or that form as well. Okay, so you could tangent squared theta plus 1 is also equal to secant squared, and 1 plus cotangent squared theta is also equal to cosecant squared theta. Okay, so again, this is the most commonly used, but you do see the other two as well. Okay, and the lesson today, again, it's really nothing new now, right? The rest of this unit is simply going to be proof, solving equations, simplifying things, simplifying expressions, yeah, things like that. Okay, so let's do some examples here. Okay. Okay, so again, you can see here, it says these identities can be rearranged. So from here, you can get this, and you can get that. Okay, you can just rearrange them, and you get these equivalent identities. They can also be used to prove other identities and to simplify equations before solving them. Okay, so here we go. Let's look at our first 3 examples here. I'll do these 3, and then I have some for you to try. Okay, so we have cosine cubed plus cosine x times sine squared x equals to cosine x. So again, here's my t-table. It's not really a table. It's my t-chart. There you go. What I can do on the left-hand side, again, 2 little tricks that we talked about last time was simplify the one side that is more complex and change everything to sine in terms of sine and cosine. Clearly, for example A, everything is already in sine and cosine. So what's more complex is on the left, so that's what I'm going to simplify. Okay, I see that both terms have cosine x in these 2 terms. Okay, so I'm going to factor cosine x out, and I end up with cosine squared x plus sine squared x. And I know that cosine squared plus sine x squared is right here. This equals to 1. So therefore, I can simplify this to cosine x times 1, which is just cosine x. And there you go, finished. Okay. Second one, part B. This one we could use, again, we could change everything to sine and cosine. Or in this case, we see that we have 1 plus tangent squared in the denominator, which we can directly apply this right away. Okay, we have tangent squared plus 1 is equal to secant squared. This is written at 1 plus tangent squared. It's the same thing as tangent squared plus 1. So we can rewrite this as secant squared x minus 1 divided by secant squared x. Okay, now here what we can do is, because it's a monomial in the denominator, so what we can do is we can divide them separately. Okay, what I mean by that is we can actually split this into 2 fractions. So we have secant squared divided by secant squared, which is 1, minus 1 divided by 1 minus secant squared x. Okay, so that's all we can do. Now from here, I'm going to change everything to sine and cosine. So we get 1 minus 1 over secant is equal to 1 over cosine squared. Okay, now if I flip over this fraction, I actually get 1 minus cosine squared x. And now from here, I do know that 1 minus cosine squared is equal to sine squared x. Okay, now you might ask, well, how do I do that? Well, that actually comes from this Pythagorean identity. If you move, what do I want? If I move cosine squared to the right, then I end up with sine squared theta is equal to 1 minus cosine squared theta, right? Notice how I just moved the cosine squared theta to the right, so then I end up with sine squared equal to 1 minus cosine squared theta. So 1 minus cosine squared x simply is the same as sine squared x. Okay, so that's the second example. Okay, the third one, this is the third trick that I'm going to show you. Sometimes you will need to multiply what we call the conjugate. Okay, so hopefully you remember what that is from pre-calc 11. If you don't, that's okay. I'm going to show you. And you use this trick mostly when you see 1 plus, 1 minus cosine x, or 1 plus or minus sine x. Okay, so when you see those four terms, for binomials, 1 plus minus sine x, 1 plus minus cosine x. Whenever you see this in a denominator, there's a good chance that you will need to multiply by its conjugate. Okay, so if you don't remember what conjugate is, it is simply the same thing, except it's now plus. Okay, so if it was 1 minus cosine, then you're multiplying by 1 plus cosine over 1 plus cosine. If this was 1 plus sine x, then you'll be multiplying by 1 minus sine x over 1 minus sine x. Okay, so that's the conjugate. It's basically the same binomial, except one is plus and one is minus. And the reason why we do this is because, I'll show you. Okay, so in a numerator, I would actually not expand this. I would just keep it as it is, like this. Okay, now in the denominator, we have, this is the difference of squares, right? I mean, if you multiply this, if you expand this, you got 1 times 1, which is 1. 1 times cosine is positive cosine. Negative cosine times 1 is negative cosine x. Notice how these two are the same, except they are negative for each other, so they will cancel out. And that's why we multiply by the conjugate, so we can get rid of the middle terms. Okay, negative cosine times positive cosine is negative cosine squared x. So what you end up with is you get sine squared x times 1 plus cosine x divided by 1 minus cosine squared x. Okay, so again, the middle terms get cancelled out. And what do we know about 1 minus cosine squared? Well, we just saw that earlier. 1 minus cosine squared x gives you sine squared x. So you end up with sine squared x times 1 plus cosine x divided by sine squared x. They will cancel out, so you end up with 1 plus cosine x. Therefore, it's exactly the same thing as what's on the right. Okay, so that's the third trick that I just showed you. So again, let's go over them quickly here. First, always reduce the or simplify the more complex side. Second, I mean for now at least, you should change most terms to in terms of sine and cosine. Multiply by its conjugate would be the third one, and I would add the fourth one here. Add or subtract fractions if you can. Okay, so I know I didn't do it here, but because I simplify first, that's why I didn't, make it a common denominator, subtract them. Otherwise, really, if you do that, you just go back to that. So there's no point of doing that. Okay, so here are the 3 examples that I just showed you. There are 3 for you to try. So good luck. All right, so I'll show you these 3 here. What I would do here is I would factor out secant x, and you end up with sine squared minus 1. Again, based on this Pythagorean theorem, I can actually rearrange this. I can move 1 to the left and cosine squared to the right. Then you get sine squared x minus 1 equal to negative cosine squared x. Okay, so, and I also am going to rewrite secant as 1 over cosine. And this, I get negative cosine squared x. Notice you can cancel the cosine x, so you actually end up with negative cosine x. Therefore, they are the same. Okay. Part B, here I would, again, that's a secant, so I'm going to change it to 1 over cosine. This is cosine, so again, I have a fraction now, so I would actually rewrite cosine as cosine squared x over cosine x. So I have the same denominator, and therefore I can do some simplification here. I have 1 minus cosine squared on the top, and I know that 1 minus cosine squared would give us sine squared x. And again, if you don't know how I got that, again, I just move the cosine squared to the right, and I end up with 1 minus cosine squared, and that will actually leave me with the sine squared x. Okay, so that's all I'm going to have for the left. On the right, I have sine x times tangent, recall, is sine x divided by cosine x. Sine times sine gives us sine squared x over cosine x, and therefore they're the same thing. Okay. The third one here, this is again another example of we should multiply by its conjugate, because this is 1 plus cosine in the denominator. So here I'm going to multiply this by 1 minus cosine and 1 minus cosine here. So you should end up with sine x times 1 minus cosine divided by 1 minus cosine squared, which is going to give us sine x times 1 minus cosine divided by sine squared x, and now you can cancel the sine x, so you end up with 1 minus cosine divided by sine x, and now you have the same expressions on both left and right. Okay, so that's the proof. Again, it just takes time to practice, that's all right? Okay, we're going to move on to example number 2, and this is about solving equations. Okay, so let's take a look. We have 3 minus 3 cosecant x plus cotangent squared x equals to 0. Okay, so right now what I see, again, when you solve equation, you must, or most likely, you'll have to rewrite them in one trig ratio only, right? What I mean by that is you can only have sine or cosine or tangent. You can't have, there's no way you can have this, okay? You can't have cosecant x and then cotangent squared x, because you can't solve equations like that when they have different trig ratios. Now, what I do notice is that I know that I can rewrite this cotangent squared x. Okay, this cotangent squared x is the same thing as cosecant squared x minus 1. And I'm going to use this because then I can change everything to cosecant x. Okay, so I'm going to rewrite this 3 minus 3 cosecant x plus, so now again, instead of cotangent squared, when I rearrange this, I get cotangent squared to be cosecant squared minus 1. So I have cosecant squared minus 1 equal to 0. Okay, and now I can actually solve this. So, well, I'm going to simplify this a little bit first. So I have cosecant squared x minus 3 cosecant x. That's a 3 plus negative 1, so it's a plus 2 here, equal to 0. Now I can factor this. Again, this is a quadratic equation. So I'm going to end up with cosecant x minus 2 times cosecant x minus 1 equal to 0. Okay, 2 times negative 2 is positive 2, and negative 2 plus negative 1 is negative 3. Okay, that's perfect. This means either we have two cases, right? Either cosecant x equals to 2 or cosecant x equals to 1. Okay, so now from here, what I'm going to do is I'm going to rewrite cosecant in terms of sine and cosine now, because to solve cosecant trig equations, it's kind of difficult. Now, cosecant is 1 over sine. Okay, so I can rewrite this as 1 over sine x equals 2, or 1 over sine x equals 1. Now, after some manipulation, then you get sine x equals to 1/2, or sine x equals 1. Now, here's the domain between 0 and 2 pi. These are both spectral angles. For sine x equals to 1, this only happens at pi over 2. Okay, so it does not happen anywhere else, just pi over 2. Again, if you don't recall, just look at this. Sine is the y value. That is the only place where y is equal to 1. That happens at pi over 2. For the 1/2, that's your special triangle. Okay, so 1, 2, root 3. This is pi over 6. This is pi over 3. So the reference angle for sine x being 1/2 would be pi over 6. Okay, because opposite of hypotenuse, opposite is 1, hypotenuse is 2, therefore the reference angle is pi over 6. So we have sine x equals to positive 1/2, and we know that we would have two cases because sine is positive in quadrant 1 and 2. Therefore, our first case is going to be pi over 6. If it's in quadrant 2, then the angle will simply be pi minus pi over 6, which is going to be 5 pi over 6. Okay, so there are your three answers right there. Pi over 6, 5 pi over 6, and pi over 2. Okay, so that's how you do this. Now you can always check for restrictions. Okay, well, I mean you should anyways. Okay, so we have cosecant. Again, cosecant is 1 over sine x. So sine x cannot equal to 0. Now, sine x is not going to be equal to 0 in any of these three cases, so I think we're fine. For cotangent, we're looking at cosine over sine, and so I think we know for cotangent, the restriction is that sine x cannot equal to 0 and cosine x cannot equal to 0, okay, because tangent is a sine of cosine. Therefore, there's the denominator cosine cannot equal to 0, and you can also think cotangent as cosine over sine, which means sine cannot equal to 0. Now, we do have cosine equal to 0 at pi over 2. So this answer actually does not work. Okay, so you got to reject that answer. Okay, otherwise you have this equation undefined. Okay, so your only two solutions would actually be pi over 6 and 5 pi over 6. Okay, so be careful. You should always check for restrictions. Okay, so again, let me say it again. For cotangent squared x, pi over 2 does not work because cotangent is the same thing as 1 over tangent. And we know that for tangent to be 0 or undefined, that means cosine would have to be equal to 0. And we know that at pi over 2, cosine is 0. So you got to reject that answer. Okay, so you should always check with the restriction. Okay, so there are two questions for you to practice. Good luck. Okay, so welcome back. Make sure you take your break if you have to. Okay, so I just got off my water break. Anyways, so for these two equations here, again, you got sine x and cosine squared. You can't solve this equation unless you change both to in terms of sine or cosine. So we know cosine squared can be written as 1 minus sine squared. Okay, you just got to manipulate your Pythagorean theorem. You get that. For the second equation here, you got tangent squared and secant squared. Again, you can't solve this equation unless you change both of them to, one trig expression. So I changed secant squared to be tangent squared minus 1. So, tangent squared plus 1. That came directly from here, right? Secant squared is the same thing as tangent squared plus 1. So there we go. Now I'm going to quickly solve these two equations here. So we have 3 minus 3 sine x minus 2 plus 2 sine squared x equals 0. You should get 2 sine squared x minus 3 sine x plus 1 equal to 0. You can factor this. You should get, I didn't leave you with a lot of room, minus 1 and minus 1. Okay, so this means sine x equals to 1/2, and this means sine x equals to 1. Oh, this is perfect. This is exactly the same thing as the one we just did on the top here. So, well, that's nice. So then I'm just going to write down the answers like what I did in the previous example here, right? I got sine x equals 1/2 and sine x equals to 1. That's perfect. What were the answers? Pi over 6, 5 pi over 6, and pi over 2. Okay, now we just need to check for the restrictions. Well, in this case, there's no denominator, so I think we're fine, right? Sine x, cosine x. So, perfect. Here are three answers. Okay, part B. Continue from here. You just need to expand, so you should get tangent squared x plus 2 tangent squared x plus 2 minus 3 equals 0. So you should get 3 tangent squared x minus 1 equals 0. Solve for tangent squared, you should get 1 out of 3. Now you can square root both sides, then you get tangent x equal to plus minus square root of 1 over 3. Okay, so now you need to find the reference angle, and that is simply the inverse tangent of 1 over root 3, or square root of 1 over 3, same thing, okay? Now I'm going to put this into calculator. Make sure I don't make the same mistake as I did yesterday. Forget to actually inverse trig ratio it. Inverse tangent of the answer in radian mode, perfect. This is going to be 0.52. Okay, and now we're looking at tangent being both positive and negative. Well, in that case, it will be in all 4 quadrants, right? So we would actually have 4 answers, 0.52. x2 would be pi minus 0.52. x3 would be pi plus 0.52, and the last answer would be 2 pi minus 0.52. So obviously that's the answer. Second one, put into calculator. So pi minus answer 2.62. Okay, round to 2 decimal places. Minus pi, negative answer. Okay, and the next one would be pi plus that. So we take pi plus the answer. This is 3.67. Okay, and the last one, okay, I'm just gonna do it again. So inverse tangent of square root, or 1 divided by root 3. Oops. Close. And then 2 pi minus the answer. So 2 pi minus answer. You should get 5.76. Okay, so these are the 4 answers. And again, you want to check if any of these will hit the restriction. And I mean, we won't, because it's not one of those special angles, so really you won't. But I mean, we can always check. Tangent is sine over cosine, so this equation doesn't work if cosine equal to 0. Now, these are not the angles where cosine would equal to 0. Okay, secant is 1 over cosine. So then again, we're thinking about when is cosine going to equal to 0, and none of these will make cosine 0. So we're okay. And these 4 answers will be our solutions. Okay, so that's it for this lesson. Again, nothing new. It's just 3 new identities, but the questions that we're doing are the same: proofs and equations. And that's what we're going to be doing for the next 2 lessons as well. Okay, so but with more identities. Okay, so there you go. Good luck with some practice questions, and let me know if you need help. Okay, bye.